Okay, hello everyone. Welcome to the Introduction to Zig workshop. Um, so I'm gonna have a bunch of content for you guys. So mainly all the actual code samples are on the wiki. So you can, I think if you scan the QR code, it should bring you to the wiki, which is the main content of this website. The slides I'm just using for a brief intro. And actually, what does content do then? Oh, content goes to like a GitHub repo with all the code samples as well. But all the code that we're going to use is on the wiki already. So you can just use the wiki link, which is the QR code. I'll leave it up for a bit more. Okay, so in case you haven't got the link down, it's right behind me or on the board, so you can use that as well. So hello everyone, I'm Raven. I'm a third year computer science student. And just a brief introduction of me, I like learning new programming languages. And I really like thinking about programming language design and the tooling that surrounds programming languages. So maybe not too much into the type theory or like compiler design or that, but just like about the experience of using new programming languages. So along this interest, I've previously given workshops on Rust and Go, and now I'm giving a workshop on Zig, which is I guess the latest language that I just learned for fun. So a little anecdote about why you should learn new programming languages. So back in 2018, Rust was pretty new, and I was like, oh, this is a pretty cool language. And at that point in time, I had done like iOS development, not really web development, but iOS development. And I was like, oh, this language looks a lot like Swift, which I'm currently using for my apps. It's like, okay, let me just learn a new programming language. So I learned something, I put it on GitHub, and then maybe a week or so later, I got an email from a recruiter. And this recruiter was a recruiter for a crypto company called 10x, now defunct. But they were like, "Oh, I see that you have used the Rust programming language before, and we want to like bring you in. We want to bring you in for like a internship." And that's how I got my first internship. Hello. Yeah. So, um, why learn new programming languages? Because number one, it's fun, and because it could open up opportunities that you never knew before. So the recruiter literally searched Rust Singapore and saw that I was probably like the most suited person in Singapore for an internship at that moment. Oh yeah, so and you should put anything that you learn in public as well. So if you want to learn new languages, there's this book called Seven Languages in 7 Weeks, and once you finish that book, um, you have seven more languages in 7 weeks. Okay, so why Zig? So I think Zig is a systems programming language. So it's kind of the most similar you can think of to C, C++, and Rust. But why use Zig instead of them? I was asked this question yesterday and I couldn't really answer it, so I searched it up today. And basically in Zig, nothing is hidden. So we can think about memory allocation, we can think about abstractions. Think about it in Rust, which is the language I'm most familiar with. Box new kind of like hides an allocation. We don't really know what's going on. When are we allocating memory? When are we not? So in Zig, this is all explicit, and that's what makes it maybe much more easier to read. And in abstractions as well, Rust, despite being like a low-level language, still has a lot of hidden magic. Think about Rust fat pointers, for example. In Zig, there's no such thing as a fat pointer, and nothing is like hidden or hidden away, and nothing is magic. And you can sort of think about Zig as compared to Rust as like C compared to C++. There's a whole different class of applications that you write in C versus C++. You might use C++ for like large code bases, maybe games or like slightly higher level stuff. But in C, you would use C for like building databases, building like maybe emulators, or building like I guess operating systems. And this is where I believe like Zig fits in. It's a replacement for C rather than C++, and just as Rust is a replacement for C++ rather than C. And the Zig author is also pretty like he writes a lot online. He gives a lot of talks, and he really thinks very deeply about like modern tooling and how to build like a great programming language experience. And so one of the big advantages of Zig, as we'll find out later, is that it's strongly compatible with C. and in fact has a built-in C compiler, which we will see later as well. So for today's workshop, I will assume that everyone has basic programming language knowledge. And I think I've asked around a bit just now. Is anyone not familiar with like the concept of, let's say, a pointer here? So is anyone like only familiar with Python? Okay, cool. So we'll skim through the basics because I think in past workshops I talk too much about basics and don't actually go to the cool parts. So we'll look at a few cool parts of SIG, which is the error handling mechanism, the memory allocation, how memory is handled in SIG, working with C code directly, and exploring this feature called comptime, which is short for compile time, which we will explore later. So feel free to raise your hand at any point in time if anything is unclear, and feel free to call me out if you know more Zig than me, because I am just like learning this as well. So if you want to follow along for specifically the C part, you can install Zig. It's quite easy. It's probably one command on most computers. Otherwise, please use zig.fly.dev to follow along, because I believe the rest of the Zig playgrounds like kind of don't work. Okay, and I guess just a disclaimer, I really do this just for fun. I have not written Zig professionally, or like have used Zig for any large scale project, and I'm just sharing what I know. And do like just shout out if you guys know found something else or want to discuss something. Oh, I didn't include a slide on what Zig is currently used for. So there's two big products that use Zig right now. Yeah, so bun.sh, recently funded startup. It's a JavaScript toolkit. It's actually written in Zig. It's actually written in Zig and not Rust, which most stuff are written nowadays, I guess. And this database called Tiger Beetle. So like I mentioned, you will want to write a lot of like low-level stuff in Zig, and this is one example. It's a database specifically for financial transactions, and it's very fast. And it's very safe as well, despite Zig being like not so safe. Yeah. Okay, so let's dive right into the wiki. So everyone should have landed on this page. Admittedly, it's kind of bare, but we can go to language basics and start talking about it. So here's a quick hello world program in Zig. Maybe I'll zoom. Is that better? Okay, so here's a quick hello world program in Zig. So in Zig, you have compiler directives, which are called with the at. So this is just like saying, okay, import the standard library and assign it to the variable standard, std, and then we just do std debug print hello world. And of course, this being like a low-level language, you must supply your own new line character. And then this is like the format arguments. So this is just an empty array right now, so you can sort of ignore that. So I'm just going to copy this and go to zig.fly.dev, and then just paste it in and run, and it should print hello world. Yay, we've now compiled and run our first program in Zig. Zoom this in as well. Okay, very simple. Anyone cannot get this working. Okay, so let's talk a bit about primitives. So as with any language, you kind of want to know like all your basic data types. So we have integers. As per usual, these are sort of like similar to the ones in Rust. We have a 32-bit integer, 64-bit integer, unsigned integers, and oh, look at this. So it turns out that Zig has integer sizes of any size. So you can do I17, I54, I whatever you want. I think up to 128, up to 64, sorry. And it will literally be of that size. Of course, when it compiles down, it will compile down to an appropriate size that like fits the computer and all that. But this is just something interesting that we will look at later on in the struct section. You can, this should be U, but you can do this for an unsigned int as well. And of course, we have floats and doubles, which are just F32 and F64. We have booleans, and we also have strings. So strings in Zig are sort of like just an array of characters. So U8 is like a char, for example, in C. It's just 8-bit. It's just an 8-bit unsigned integer. And then we have a slice, which we'll talk about later, but it's, in essence, this is how a string is represented in Zig. And then we can sort of do the same std debug print. And now you see that we pass in the argument of integer into the print function, and then we just use this to represent the argument. And if I copy that and run, oh yeah, so some of the examples don't have the main function for the sake of brevity. So we can just, okay, I'll just type this out. Actually, wait. Okay, so you would just like paste it in the main function that we previously provided. Okay, and we can change this to U and run. And you can see that everything prints out as expected. So of course, unsigned means you can't use negative numbers, but signed means you can. So you can see that floats print out in this sort of weird way. This is just like the exponent. So in this case, the exponent is 0, so this is just 3.14. And strings print out as expected as well. For strings, when you print them, you just want to use the S, like format specifier. Of course, if you want to print out 2 integers, you can just print like 2 of these, and then you just do that, and then you can run that as well. Oh yeah, if I haven't said this before, and you're encouraged to follow along and then try out different things. For example, maybe you can try turning this to 19 and just to verify that I'm not trying to trick all of you, and yeah, it's a 19-bit integer as well. Oops. Okay, so that's very simple stuff. Ints, floats, boolean strings. Let's move on to arrays. So arrays in Zig like have a fixed size. And there aren't many differences between Zig arrays and those found in C and C++. So you specify arrays like this. So you have my int array, and then they have a size in front. And then you have I32, and then you just literally specify what is in the array. You can also use this underscore character to sort of infer the size. Don't miss out the underscore, don't miss out whatever's between the brackets, because that will turn it into a slice, which we'll talk about later. So this is specifically arrays. And when you print out an array, you just use the any modifier. And yeah. So you can also access the length of an array by doing array.length. And that's sort of like the only field you can find in an array. And this should print out the correct length of the array. And similarly, as we all should like know in C, C++, Java, you just like access it by using the brackets as well. So arrays are like copied by default, which means that if you assign an array to another array, and Zig has type inference, so you don't have to specify that this is an array, you just assign it, and you modify it, you can see that it will not have any changes. So let me just run this to show. Yeah, you can see that the copied array has no changes, while the original array would have changed if you try to print it out. So one thing that's interesting about arrays in Zig, and a slight departure from the other languages, is that we can specify sentinel values. So sentinel values are sort of, you know how in C you have strings, and your strings have a value, your strings in C always end with a 0/0 character. Okay, if you don't know that, basically sentinel values are, you specify a value after the colon, and that's what ends the array off. So if I just print my sentinel array, it will print 1, 2, 3, 4, 5 here, right? And if I access it with length, it will print 5. But if I sort of trick the compiler and say that, hey, actually this array is like, has 6 values inside, you can see that the 0 is actually like at the end of the array. So this is different from just directly having this, and we'll see it come in useful maybe a bit later, but this is just a fun fact. Don't worry if you don't understand it fully. But yeah, so if you specify 3, and I run that, you can see that later my array actually ends with a 3 in like real memory over here. Okay. So that's arrays. It's kind of simple. They're all fixed size, and you can't change the size, you can't change anything, and it's all built into the array type. Let's move on. Before we move on to slices, let's move on to pointers first. So Zig is interesting, and it sort of fixes a problem from C and C++, where we actually specify whether a pointer points to a single value or a pointer points to multiple values. So in C and C++, you kind of just have int star, and that points to either a single integer or any number of integers, and you don't really know what's the intention of this pointer. In Zig, however, we have star int, star i32, which is like a pointer to an integer, and we also have this syntax. So you can see that this is single and this is many, and you can see that it specifies this specifies that the many int pointer is actually pointing to many integers instead of just one integer. And if you see, we actually get that pointer from referencing an array, which is many integers. So if I just, for the sake of it, I'll just run this example, format, and run. Yeah, okay, so this is an interesting thing. So you can see that I create here a pointer to, okay, so to create a pointer first, you need to sort of reference the actual value. So this is a pointer, some int pointer is a pointer to some int, for example. And you can see that it's a memory address that stores an i32. Here I'm creating an array of 3 values, and I am getting a pointer to the first value in the array. Okay, so I'm referencing the first value in the array, and for the many int pointer, I'm just straight up referencing the array. And if you look at the console output, you can see that it's literally exactly the same memory address. They're both pointing to this over here. But yeah, you can see that it's literally the same address. However, there are actually two different things. There's two different intentions here. One is to point to an array of values, and one is to point to a single value. And this distinction comes in very useful when you are doing much lower level stuff like communicating with C. So just like arrays, pointers to multiple values can have sentinel values. So you have an array of 3 and then with 0 behind. So you can imagine there's like a virtual like 0 here. Oh, okay, you can't do this kind of command in Zig, I guess. Okay, imagine there's a 0 behind. And now when I get a pointer to that array, I actually have to specify that it ends in a 0 as well. So if we try to print this, you can see that well, Zig is unsafe, firstly, so you can access you can access multiple, like a many pointer by using the normal array syntax. And you can see that the third element of this array, the fourth element of this array is actually 0, which is the sentinel value that we talked about earlier. Yeah. So if I do 2, just to prove that it works, we should see 3, which is the third. And if you do 3, you should see 0, which is the sentinel value. Let's see what happens if you try 4. Run. I think it should crash. Okay, I think it crashed, but the playground is bad. Let's try this. Pointers. Okay, so let's do the same thing in my actual local instance. Zig run 4. Oh, okay. Guess it doesn't crash. Okay, so point here is that Zig is unsafe, so don't do weird things. And okay, so as an aside, notice that this type, and a pointer to many unsigned U8s, unsigned 8-bit integers, is actually literally the same type as strings in C, right? Because we have a pointer to many characters, and that character list ends with a 0. And that is literally the same as a C string. So this is super useful when it comes to talking to C that we'll see later on. But yeah, so this is something cool that we have. We have an exact representation of a C string, which is very different from, let's say, we're using Rust and the C, FFI, and Rust, and then we have to use a lot of like unsafe coercions. Don't know how to pronounce that. Coercions. Yeah. Okay, so at this point, is anyone have any questions? Does anyone have any questions?
Can there be multiple sentinel values?
No. So you can only have a single sentinel value. Yeah. Anyone with Google, correct me if I'm wrong, but I don't believe there should be many multiple sentinel values because yeah, it's intended to be a single value.
Is there a way of dereferencing?
Ah, yes, correct. So I missed that out actually. So to dereference, I'll use my local instance just to. So to dereference a pointer in, for example, for sum int pointer in C, you would do something like star sum int. Deref pointer. Let's print that out. So this should be a value, and then we can just print out deref pointer. And then we can try doing that. You can see that, of course, it doesn't actually work, and it gives expected type. This is just sort of saying that I kind of expected a type here, but it's at I32. So the actual way to dereference is slightly different. It is dot star. So this comes with some intention, but I won't cover it here because, I'm trolling. Okay. Yeah, so this comes with some intention of why it's this way, but for now we can just assume that this is the way to dereference a pointer. Okay, maybe as an exercise to everyone who has it open, you can try to dereference many item pointer. So like dereference this one and see what happens. Okay, so moving on, we now move to slices. So for those of you who are familiar with Go, this is pretty much the same concept. So in terms of slices you can treat as a view into an array. So this is quite similar to Python slices as well, except that in Python we have like a slice of an array is still an array, but in Zig we treat it differently in that slices have a dynamic, quote unquote dynamic length. So we don't specify the length of a slice inside its type. Instead, we sort of like just have a slice with an unknown length that we can access via dot length. So a slice is literally two pointers, two 64-bit integers on a 64-bit system. The first being a pointer to the first element of the underlying array, and the second being the length of the slice. So if I run this, if I go to slices, so if I run this, you can see that our slice of 2 to 6 of this array of 1 to 10 is actually just 3, 4, 5, 6. Of course, because array start is 0. And you can see that the length of a slice is actually 4. And you see that the slice also has the dot pointer value, field. And this pointer is actually literally the same as referencing the second element of some array. So remember how we did, we access the slice this way. So it starts off at element 2, which is 3. And it has the exact same pointer to that as the array itself. So some slice the pointer equals, this one is true. So you can think of slices as actually just another way to point to an array and to point to somewhere within the array rather than just the start. So if you modify the slice, because you're modifying through a pointer, you will actually modify the underlying array as well. So you notice if I do some slice and I modify the third element, it actually modifies the third plus 2 element of the array here. Slices, you can slice slices as well. So you can have sub slices, and just like arrays, slices can have sentinel values as well. So you can explore this further, but this is literally almost the same example as earlier, except that notice we don't have a length in the type anymore. Okay, so that's for slices. Okay, so this one is the very normal part, and you will probably know already. You can use a if-else statement in Zig. It's if else, the same as like C and C++. There are slightly different if statements that we'll see later on, but this is literally the same. So I will not try them out. Maybe one difference is that you can use if-else as expressions. So you can use it on a single line if you don't have the curly braces. If you have curly braces, you can't use it on a single line, but correct me if I'm wrong. Yeah. So we also have switch statements. So switch statements are slightly better than the C variants, where you can do switch on, I guess when you're switching on integers, you can switch on ranges. And the last clause is an else instead of like a default or something like that. And we use the arrow instead of a colon. You don't have to break on every case of the switch statement, unlike in C. And I don't believe there's a fall through mechanism as well. So each branch is basically its own thing. Similar to if statements, if you don't use the curly braces inside, you can use switch statements as an expression and then get the result as a value. So this comes in really handy sometimes. So it's good to know actually. Okay, so other than that, there are more complex switch statements. So this is just the most basic one. It literally is switching on a value. There'll be more complex ones that we'll see later on. And the while loop is literally the same, except with you can pass an expression after the condition. So this is sort of like the for loop in C or Java or C++. So this just executes after every iteration. So you expect this to print 1, 2, 3, 4, 5 all the way until 31. 31. Yeah. For loops, on the other hand, have quite a different syntax. And for loops are literally used just to iterate over slices. So and arrays. So you can literally for an array, and then you can capture sort of the variable in these like bars. Not sure what exactly you call them, but these bars, and then you can use the item as you expect. So this will print 1, 2, 3, 4, 5. It works on slices as well, and you can iterate over pointers to each element, so you can get a pointer to item instead of item itself. And so this comes in useful when you want to modify things in the array. So I'm going to show this. So we have zig run 0, let's see, 9. Yeah, you can see that it iterates over the pointer, and if we do item dot star equals to like 50, oh, shit. 50, save and then run, you can see that our slice turns into 50. So maybe one more useful thing that you can try, which is not in the wiki, is that you can actually specify multiple slices. So you can do some other slice, and however both slices, and you can do like other item as well. So this works, and you basically iterate over both slices, but you need them to be the same length. Otherwise, I believe it will crash, or if not, it will give weird things. Yeah. So one more useful thing is that if you want the index of the item, you can actually do 0 dot dot, and this will return you the index. Slice item like this, and if I believe I do this, this will give you the index. Yeah, 0, 1, 2. I think if you start at 2, it will give you 2, 3, 4. Perfect. So yeah, something to try. Okay, so now we'll move on to, before I continue, does anyone have any questions on everything we've covered so far? They're always mutable. So if you want a pointer, let's say const some pointer to i32. So this is mutable, and you can do like some pointer, can't type, dot star equals to something. If you want them to be immutable, you specify const in between. Yeah, so this is an immutable pointer. Also worth specifying is that you need this to be a var for it to be fully mutable. Yeah, Yeah, I'm not talking about const versus var, but you can explore that on your own. Usually the compiler gives you the correct error message, then you just change accordingly. Okay, so any other questions? Okay, cool. So now we'll talk about structs. So structs are quite similar to C and C++, and they're kind of like classes in Java. They're just ways of grouping data together. So if you can see here, point is a struct that has two fields, an x and a y, and a rectangle has two fields, which is the top left point and the bottom right point. So notice that it's very interesting, right? Like the syntax that we use is literally the same as assigning a variable. Const point equals to a struct, and we'll explore more on that later. But for now, this defines a struct and this defines a struct, and you can define methods in structs as well. So if you do your define functions inside a struct and you specify the first argument of that function is the struct itself or a pointer to the struct, then you have a method. So you can do rect.area, for example. So to demonstrate this, we can look at the example where we have var point1 equals to 32 and 32. So the syntax of initializing a struct is probably the most unfamiliar thing here. It's literally dot, then the field name equals to something. In fact, this syntax actually comes from C, and you can initialize C structs in this way. This was a TIL for me when I was learning this. So then you have another point, and then you have the rect, which is the same initialization logic. And then if you print all of that out, it should print the correct thing. So otherwise, it's kind of the same as you expect. You can do point1.x, rect.bottomright.y, and it should all give you what you expect. Methods are also very similar. You do rect.area, and notice there's no parameter here, and that's because that's self. And then you call it as a method, and then you just pass, you just get the correct area. So structs are copied by default. In fact, everything is copied in Zig. So if you just assign, yeah, so you notice how if I do point1.x, and maybe this is better demonstrated. Notice how if I change point1.x to 99, it will change to 99. However, point1 that was used in rect isn't changed. Yeah, and that's because when we specified point1 here, it was copied into the rectangle rather than like, if this was like Java, this would actually change because Java does pass by reference. But in this case, everything is copied. Very simple, don't need to think about it. This point1 is no longer, this top left is no longer point1. They are just two different structs. You can't. Yeah. So it's if you want to sort of pass a reference, then you will just pass a pointer to the point. Right. Yeah. So it's very C, C++ vibes. Yeah. Okay. So that's structs. Any questions on structs? Okay, I would recommend exploring this further. Admittedly, I could have talked more about methods, but I think these are quite self-explanatory. You can experiment by turning this to a pointer, for example, and then we see what happens there. Yeah, I guess because this is not a pointer, self is actually copied here. So if you modify self.x equals to something, it won't actually change the rect that you expect. So you can experiment with that on your own. Okay, so following that, we have enums. So enums are literally integer values, a bunch of integer values. So for example, we specify a color enum that has red, green, blue, yellow, brown, and under the hood, although not explicitly, this actually turn into 0, 1, 2, 3, 4, 5. So it's literally just a bunch of integers. You can specify what size of integers you want. For example, I believe this will turn into a 64-bit integer, but correct me if I'm wrong. you can specify you want 8 bits instead of 64 bits for maybe performance reasons or size reasons, whatever. And then you will have only, like, I guess, 2 power 8, 256 possible values for this enum. You can do any integer here. And then you can explicitly say what you want the values to be. In this case, they're all ascending order, but I can change this to like 25 and it'll still work. And for example, enums can also have methods. So in this case, we're taking self, and then we are returning a string. So this is the string type in Zig, and we're saying, okay, we switch on self, and this is where the more complex switch statement I talked about earlier happening. It's just literally .add. You can do color .add here, but this is just a shorthand. So .add, return add, return sub, and so on and so forth. Let me copy, actually, wait, let me just bring this up. Maybe one interesting thing that we talked about earlier is that I can actually remove the returns, remove the returns here and return it here. And this works as well because the switch is an expression. Run, maybe just to prove my point. Yeah, still works. Okay, so now we can also, so you can use enums and switch statements, color.red, and then you switch on some color, and then you print out the appropriate color, and you get the correct value. Yeah.
Must the value in the enum be an integer?
Yes, so
So you cannot use floats. You cannot use.
no, I believe that you can't use arbitrary types. You can only use integers. But do Google that as well. I'm like 80% sure. Yeah, I checked it yesterday because I was curious as well. Okay, so that's enums, literally integers. And maybe the most complex one, I believe, yeah. So the most complex kind of data type we can use are actually unions. So unions are a way of saying that, so you know how in structs, when you have two fields, you will have both fields in the struct. You have both x and y in the struct, for example. Well, in unions, you're actually saying that I want all my fields to occupy the same memory address, the same like place in memory. So in this case, for example, a shape union is only either a circle, a rectangle, or a square. It is not a circle and a rectangle and a square, unlike a struct. So if I turn this into a struct, it'll be circle, rectangle, and square. But in a union, it's only either circle, rectangle, or square. Yeah, you can see that. So the syntax is nearly the same. It's just called a union, and this is very similar to C unions. And you can see that I'm specifying that circle is actually a struct with a radius, and rectangle is a width and a height, and a square has a size. So a shape will either be a circle with a radius, a rectangle with a width and a height, and a square with a size. Yeah, so the whole point of this, I guess, is you remember how we used enums just now? So sure, we can do a shape enum, and then it can be circle, rectangle, or square, but we can't store any information in there. So in order to store information, you would want to use a union instead. And let's just try this first. I will talk up to this point. I believe 012. Yeah. Okay, yes, I have examples here. Okay, so you can see if we try to do this, so notice how like when we create the shape union here, we are saying that, okay, my shape is going to be a rectangle with a width and a height. And how do I get that width and height? I literally do some rectangle, dot width, some rectangle, dot height. Literally the same as a struct that we did just now. But what happens if I try to use some rectangle as a circle? So if I try to do that, it will crash, compiler error. And it says that, actually no, it will crash at runtime, and it says that, hey, your rectangle is a rectangle. It's active, right? You can't use it as a circle. So this is the reason, this is the whole point of a union. It can only be one of the 3 fields, and it will not change over time. It will literally just be a circle, be a rectangle in this case. Okay, so let's say we have the shape union already, and it's a circle. How do we, like, let's say you don't know this. Some shape is like passed in as an argument in a function, some shape union. right? How do you know what shape this is? How do you know whether it's a rectangle, a circle, or a square? Cool, just now in enums we use a switch statement, right? So we try to do the same thing. Okay, and then we try to run that. And we see that. Switch on union with no attached enum. So the thing is, when we declare a union, we don't actually store what like the value is. We don't actually store whether it's a circle or a rectangle or a square. So when you receive like a shape union, you don't actually you don't there's no integer or anything that says like which type is this. So in C you would have to do this explicitly, and this is called tagging a union. Yeah. So in Zig, so in C you would literally have to create a struct and have a tag and store the union beside it and so on. But in Zig you can literally tag a union by, remember the shape enum that we declared earlier? You can tag it by literally passing in as like sort of a parameter to the union keyword. So this is our tagged shape union. And now you see that the same syntax, comment this out, the exact same syntax. You notice there's no difference between these two except for we're using a tag shape union now. Now we can switch on whichever one we want and then do the appropriate code according to it. To demonstrate this, I run this, and you can see that now everything works. I'm curious what happens if we disobey what we said. So if this is a circle, we do rectangle and width. And of course, it gives the exact same error, which is, oh, it's not active. Okay. So that's unions. So we have structs, we have enums, we have unions, and that's how Zig composes like a bunch of data together. Anyone has any questions on this or like wants to try something out for the whole workshop?
So is the point of the union like interfacing Go?
Kind of. So it has slightly different purposes. One is to like sort of encapsulate behavior in Go, but in Zig it's more of to just literally store multiple possibilities. For example, let's say you have like a file, right? But you want to store, this file could be stored on disk, or this file could be stored in memory. And you kind of want to have just one variable called file that can possibly execute code for the two different things. So you would create a union file and then maybe do it like, so like union file, const file equals union, and you do like on disk and then something, or like in memory something else. Yeah. And then you can switch given any file. Yeah. Any other questions? Okay, cool. I realized, so I was doing the content for this, and I realized the whole time I didn't even talk about functions. So here are functions. They're pretty simple. The return type is at the end. It's weird, I know. Yeah, sure. Any questions on functions? Okay. You don't. So you can't, yeah. So you can pass pointers to functions. That's a good question actually. Thanks. So functions. So if I do foo right here, right, const bar equals to foo, I believe yeah, just do this to silence the warning. Yeah, you can see that this is bar is actually the same type as foo, which is I32, F32 returns F32. Yeah, but you can't actually create closures because Zig doesn't support that. So closures, C doesn't support that either. Closures are actually a abstraction. It's actually kind of magic how it captures the environment, right? You know how like closures you can reference variables from outside. So going back to what I said at the start, like there's no hidden abstractions here. If you want to do like closure like logic, you do it explicitly. Yeah. Exercise to the reader. Yeah. Yeah. Okay, so one more key thing that I didn't cover, yeah, one more, is optionals. So for optionals, you can specify, you can put a question mark in front of anything, and that will make it nullable. So by default, you can't say like sum in equals to null, avoiding the what $1 billion problem or $1 billion mistake or something. You can only null things if there's a question mark in front. You then check if something is an optional by using an if statement and then extracting the integer inside using the bars. Um, Pretty self-explanatory. You can use this very funny or else keyword to unwrap an optional and give a default value. So it's if it's null, then it just gives 0. And you can just straight up unwrap stuff by using dot question mark. And this is like, remember how we talked about dereferencing had that kind of like dot star syntax? I think is to make it quite as similar as possible to this unwrap syntax, which is dot question mark. And we will also see dot exclamation mark, I believe, which does a different thing. Yeah. You can try to unwrap a null, which is uncommenting this code, and you'll see some funny, you'll see it crash probably. It's worth noting that optionals are not free. So you can't just straight up store whether an i32 is now within the same 32 bits. So if you try this, it will turns out that optional i32 is actually 64 bits, where the other 32 bits is used to store like 1 or 0, whether it's optional, whether it's null or not, basically. However, it is free when you use it with a pointer. So question mark star gives you optional for free. We can talk about why during the break. Like if you want, you can just ask me why, or you can search it up.
What's the size of I-35?
Good question. Let's try. Maybe I'll use the playground.
See, now it's always
Size of returns in bytes. So in this case, it rounds up to 64 bits.
What if you do the question mark?
Oh, interesting question. Okay. Yeah, 35. Oh, okay. Interesting. It goes, so it rounds up I-35 to 64 bits, and then the optional doubles it again to 128 bits. Yeah, it is. But it's probably faster for performance reasons or whatever, right? I don't know for sure. Yeah. But good point. Maybe you can. Zing is open source, by the way. You can contribute to it if you want. Yeah. Yeah. Okay. Any other questions for basics? Okay, so we'll cover error handling, and then we can take a quick break. Oh yeah, sorry.
So in like I think in C like for now like they only refer to like noun pointers like, but in Zig like you can have noun for values as well. Like just now like you can there's a difference between the noun for question mark, especially like question mark I-32 and question mark asterisk I-32.
Yes. So in C, a null usually refers to null pointer. There's no like null value. Yeah, yeah, correct. So in this case, we have null value. Yeah. And null pointer just happens to be a pointer to a null value. You can think about it that way. Yeah.
So if you have a question mark, any type can have the corresponding null value.
Any type, like you sort of add on like a null value alongside all the other values of that type. Yeah.
Thank you.
Okay, so now we'll move on to error handling. I think this will be quite quick. Maybe not so quick. Okay, yeah. So notice how notice how in our main void we have this exclamation mark. So this actually means that main could potentially return an error. So if this wasn't the case, that means main cannot return an error. There is no way that main will ever return an error. Adding an exclamation mark says that it can return an error. So maybe we start with defining errors. So errors are defined in a very similar way to an enum, and in actual fact that errors are actually just a special type of enum. I guess, yeah, it's literally an integer as well. In C, you would usually like sort of say, in C we use like error codes. So like an integer as an error code, and then you just have a bunch of constants to refer to what error this is. So it's a very similar concept here, except that we actually give names to these integers. For example, an out of memory error, an end of stream error, and so on. Now, you know how like errors sort of build up. Your lowest level function can return some error, and then it propagates upwards and it propagates outwards and so on. So we actually have this operator, the OR operator, to combine different error types together. So, for example, this no EOF error, which is actually from the standard library, you can search this up, is actually a read error or end of stream. And for example, in dynamic library.zig, these are real errors. It could be file too big, not an ELF file, so on, and then it could be a POSIX, underlying POSIX error as well, and an MM error. So these literally just combine. It's literally the same as like writing them all in the same error like brackets. So after we've defined the error, how do we sort of return an error from a function? So it's actually quite simple. You literally return it. So for example, in my function can be read as it takes in an i32 x, and it returns either an i32 result or an error which is only these three possible errors. So if you encounter an error condition, you literally just return it, and that returns the error. Or if you have a result, you literally return the result. So maybe this is the point where Zig has the most magic, which is that errors are treated sort of like their own class of values. Like errors are like its own like sort of version of values. So returning this and returning this is actually completely different. One is an error, the other one is a value, the actual result of the function. It's also possible to just straight up infer the type of error, which is the same thing as the exclamation mark void that we saw earlier for the main function. And this just says that, okay, compiler, you go and figure out what possible errors my function can return. Yeah. So the reason you would not want to do this is, let's say you're writing a library for other people, you're writing code for other people. If they see this, they will not know what possible error your function can return. If they see this, it's very clear what can possibly go wrong. And Zig also has the any error type, which is literally any error. It's a union of all the error types across your entire Zig program. And there's a few cool ways to handle errors. So the first one is to be lazy and just throw the error up the chain. So this is similar to the question mark operator in Rust, but basically you're just saying if my function fails, just throw the result. Try this function, and if it fails, just return the error like upwards. Yeah. So that's the try. Otherwise, you can catch it. So try and catch do not go together in Zig. If you want to catch is used to catch an error like inline next after the function call, and then you get the error using the bars. The bars are sort of treated as like extracting a value. Like you can see extracting an optional, extracting an error, extracting an item from a slice. That's the general idea behind it in Zig. And then you can switch on the error. As I mentioned, it's literally the same as an enum. And then you print the reason. Yep. No, so the catch here is completely separate from the try. There's try and catch don't go together. You don't need to have try to have a catch. So let me demonstrate. No, you can have try without a catch and a catch without a try. Like, so for example, I can just do this. Okay, of course I must define my function. Let me try that. Okay, so I have my function above. I run this. Oops. Yeah, see, so there's no catch. You just try. So try is just sugar for saying catch error, return error. This is the same thing. Okay, if you fix obvious syntax errors. Yeah. So this is the same as just saying try. Uh-huh. You don't have to have a catch at all. So I can do yeah. So the answer to your question is yes. You don't have to have one catch for each try, but you don't have to have catches at all. You can just do this. Yeah, sure. Like they are two completely separate concepts. Yeah, so there's no catch in this function at all. It's not the same as like your try catch in like Java or whatever. Yes. As in, sorry, what do you mean by redefine the error type? Yeah, you can't. So the way you would do that is to use the catch. So there's no try. You don't need to indicate there's a try. You just catch, and then you switch on the error to check which error type it is. So is it like a dot, end of file error, or like a dot? Yeah, correct. So you can, it's like sort of magic, like global namespace, like any error that, where is it? Yeah, you just sort of catch, like figure out which error it is like this, in the by using a switch. No, this catch is not catching this error. It's a completely separate concept. So I can just have this. Let's see. Like there's no try, just catch. And it works. So like this is sort of like a different, like I guess erase all notion of try catch in other languages is unrelated. It just happens to be the same keyword. Correct. Yeah. And the error for this function. So you're catching any error that happens within my other function. Yeah. Yeah, I guess you can say that. Yeah.
So that means, let's say you have three functions and you have code that had like the three functions will throw the same error. You need, if you want to have a combined block to handle the same error, like you need to wrap all the three functions in another function.
Yes, correct. So you would want to do that. I see what you mean now. Okay. So yeah, so either you catch 3 times.
But there will be duplicate code in handling.
Yes, correct. So if you catch 3 times, if you do it like 3 times, yeah, then you would like you'll be kind of ugly. So you would sort of take this and then put it in a different function. Yeah. Good point. Good point. Okay, I see what you mean now. Okay.
Is it possible for a function to have multiple error types or they can't?
You, you can. So if you have two error types, for example, my error and what's another name? Okay, your error, Bear's reason, sure. Okay, then you can actually do what your error. I think that you don't need brackets here. I mean, I think that you need brackets here. Let's see if that works. Correct, yeah. So you can actually just do this. Yeah. Then it'll work. I think it died, so I don't think that's correct, but yeah. Yes. So okay, that's all for now. Hopefully it's not too boring. In the next remaining hour, we'll talk about more fun stuff. But in the meantime, you can ask me questions and we have a break with food and bubble tea. Oh yeah, so for those who actually installed Zig, I apologize. I realized I didn't explain how to run programs. So you would just create a Zig file, for example, 012unions.zig, and you just do Zig run. So Zig build run is a completely different thing, and you shouldn't be using it right now. I will explain how to use Zig build run later, but for now, just Zig run, then the Zig file, because we're only using single files now. Of course, if you want to use the playground, it's zig.fly.dev. It's not the other one, zig it. Yeah, it's not this one. I think this one doesn't work. Not zig it. Sorry. Zig play. Yeah, it's not zig play.dev. Boo, this one doesn't work. Yeah, it doesn't work. Okay, let's start. So that was error handling, and in the remaining like 40 or so minutes, I'll just cover the three other concepts. With the last one being my personal favorite. So stay till the end. Ooh. Okay, so memory management is handled manually. So when we talk about memory management, we are not really talking about memory management in general, because I guess memory in the stack is kind of like done automatically for you already. We're talking about dynamic memory, where we want to allocate stuff, like a dynamic length of memory that we don't know at compile time. We only know it when we actually run the program, how much memory we need. And we allocate this memory on the quote unquote heap, which is what the package that everything is stored in. So we are talking about heap memory now. So allocation in memory allocation in Zig is completely explicit. You are very, very clear when you are allocating memory, and for reasons I'll explain later. So it just follows the no magic principle. So everything is explicit, and allocation is handled by an allocator. So an allocator struct allows you to allocate memory. So the struct defines methods to allocate and free memory based on some strategy. So in C, you have malloc and free. For those who know C, you have malloc and free, and that is sort of a single strategy for your entire program. The thing is, there are many ways to allocate memory and to manage memory in that way. And Zig allows you to choose which strategy you want, which is why you have an allocator struct. For those of us who are familiar with Java, this is actually your interface, quote unquote. So if you know the details, you actually store a vtable in the allocator struct, and you have different, like your vtable could point to a different strategy depending on what you want. But if you don't know that, it's perfectly fine. You can use different allocators based on what you want. So maybe I'll just zoom out a bit. Yeah, so I'm going to talk about 4 allocators today. So these are all like different strategies to allocate memory. And then I'll talk about sort of how we use an allocator. So firstly, Zig has a general purpose allocator. And as the name implies, you would generally use this for most things. So for example, here we are defining a general purpose allocator. The syntax is quite a lot of like curly braces. I'll explain everything. You'll understand it by the end of this session. But for now, this syntax sort of constructs, like this is a struct, and then we're sort of constructing it without any fields because it doesn't need any. And that's our GPA, general purpose allocator. To get the actual allocator struct from the GPA, we do GPA.allocator, and that gives us the allocator. So now there are two functions on the allocator that we use, alloc and free. So in this case, we are actually doing allocator.allocate 16 8-bit integers. So this is 1 byte, so we're actually allocating 16 bytes of memory here. And alloc returns a slice of those bytes. So you know where the bytes start and you know the length of those bytes. So then we use a function called copy forwards to copy a string into those bytes. So remember how we talked about a string in Zig is just a slice of a certain number of bytes. So the reason why I put my here is to make it exactly 16 bytes. So when you copy this in, it copies hello my world into this memory. And then when you print it, it will print correctly. So let's try that out. Memory, GPA. So if you run that, you can see hello my world, everything works. Hoorah. But wait, didn't we just say that like we are manually managing memory here? How come we don't need to free the memory? So before talking about that, I'll talk about a brief like digression into defer keyword. So there's a defer operation which is exactly the same as the go defer operation in Zig, which basically says at the end of the current scope, execute whatever is after the defer. So demonstrating here, defer. Yeah, so it says print normal statement 1. So this is literally a normal print. Defer this print. Oh, crap. Defer this print, then print again, then defer this and defer again. So notice that when I run this, when I run 017 defer, our defers are printed in reverse order. Yeah, so whatever we deferred first prints the last. To me, it kind of makes sense, but I guess you can just remember this. Don't really have an explanation. Yeah. Okay, so that's defer. Very cool. So going back to the example we gave earlier, I mentioned that, hey, we're not freeing the memory that I allocate, right? So it turns out that the example is not complete. So that was completely fine because our program just sort of ran and terminated immediately, and the memory was just returned to the operating system. So it didn't really matter. But let's say we are doing a long-running operation like a web server. The thing is that will have caused a memory leak. And memory leaks are bad because our memory, if this function is called like 10 times, we're actually wasting 160 bytes. We're leaking 160 bytes. And if it called a lot more, then it will waste a lot more memory, leak a lot more memory. So we can use the defer keyword that we just learned to help with this. So the thing about a general purpose allocator, and the thing that's quite cool for those of us who know how to who have manually managed memory before, is that it actually has a built-in leak detection system. So it can detect leaks for you. So if we copy this example, so we haven't changed anything yet, apart from the fact that we de-initialize the general purpose allocator at the end of the scope. How do we do it at the end? Well, we defer it. So this is, because dinit returns a value, we just need to assign it to underscore to like silence any warnings. Yeah, compiler will ask you to do that, just do it. So probably 018. So notice that this is a leak. This is a leaking function. And if we run that, whoa, it says that memory address so-and-so is leaked. And amazingly, it actually tells us the exact line where we allocated the memory that we didn't free. The reason this didn't happen earlier is because we didn't de-initialize the general purpose allocator, which is like literally, it's like double error, right? Like we didn't even try to check for the leaks, so that's why it didn't tell us a leak. Yeah. So when you de-init, so at the end of this scope, basically de-init should have, it's like sort of caught here because of the defer. It will actually check for leaks, and then this is what happened. So it printed, and then it de-initted, and then it caused an error. Very cool. So now we can learn how to free memory, and it's actually really, really simple. We just say free, and then we pass in some bytes. And again, we use the defer keyword here. So this is sort of a pattern in Zig, and something that probably makes a lot of sense as well, is that generally when we allocate memory, we defer like in the next line, we free the memory. But because obviously we don't want to allocate and free immediately, we can actually defer the freeing to the end of the scope. So this pattern you will see almost everywhere. When you allocate something like directly, you will free it using a differ. As an exercise to the reader, you can also there's also this thing called error differ. You can figure out what it does. So alloc and free often come in pairs. And notice that this during alloc we actually get a slice. If you just want to allocate a single value, so let's say you have a big struct, you can just do some struct and like let's say my struct, and then you can do allocator.create. And this returns one, a single value. So this returns a slice. If I do alloc, I will specify the size, and then this returns a slice of structs. Or you can just specify one. Yeah, and then we will do defer allocator.destroy instead of free, and then my struct. So this one will be defer free some bytes. So alloc and free, create and destroy, init and deinit. Those are the general patterns that we see in Zig. Okay, so this is a general purpose allocator. I am not too sure what algorithm they use under the hood to allocate memory, but you can Google that. Should be pretty easy to find. Let's talk about other allocation strategies. So in this instance, we have a fixed buffer allocator. I believe this is just a bump allocator. So it takes in a slice of bytes. A slice of bytes. In this case, I have 16 bytes in the memory. It can take in like 1,600, any amount that you want. And then you pass it into the fixed buffer allocator.init, and in this case FBA, and then you just do the same thing. The nothing else has changed, allocator, and then see once you get the allocator struct, everything else is the same, because everything is just that same allocator struct. Alloc and free, create or destroy, whatever. Literally, this code is actually the same. We don't need to deinit anything here because there's no logic that you need to run at the end of a fixed buffer allocator. Yeah. So what a fixed buffer allocator does, I believe, is it just takes in the slice, and then every time you allocate something, it just sort of increments a pointer to the next available like sort of memory. Very simple. Usually used, like I rarely use this. Arena allocator. So arena allocator is very interesting. Arena allocator wraps an existing allocator. So in this example, let's create an arena allocator now. Arena allocator and dot init, and you notice that arena allocator creates just takes in a child allocator. So what this arena allocator sort of does, and the whole idea of an arena is that you want to make a lot of allocations, but you don't want to free them. Like you just want to do a lot of stuff like inside this quote unquote arena, and it sort of builds up. And then at the end of maybe some complex logic, for example, maybe you're compiling some C code or whatever, at the end of it, you deallocate everything at once. You free everything at once. So in this case, the arena allocator doesn't actually want to change the strategy of allocation you're using. It's just going to say that at the end of my arena's lifetime, I just want to deallocate everything. So you actually pass in a GPA. You pass in. You pass in the allocator struct. So this is wrong. You go down here. And then you pass in the allocator. And then you again do, so this is the GPA allocator. And then this is the allocator. This is the actual allocator that we want. Right. And then everything remains the same. So now that we know that this is an arena, this is useless. Like if you check what an arena allocator does to free things, it actually doesn't free anything. Right, so we don't need this. Instead, what we need to do is that we need to defer arena.dinit. So the whole idea of arena is that at the end of this scope, we just free everything at once. Everything that we've allocated through this arena allocator, we free it at once. And this is very useful when you're dealing with things like cyclic data structures, You don't really care about your memory buildup. It's just that you want to throw everything away at the end and so on. And this is what an arena allocator is used for. Okay. So beyond this, we also have page allocator. So this is actually literally the OS allocator. When you allocate like even like 16 bytes on this page allocator, it literally requests a page of memory from your OS. So usually what happens is that there's an allocator chain, right? Like your general purpose allocator will use another strategy under the hood that's using another lower level strategy. And most of the time you'll end up at page allocator, which sort of takes a page of memory from your operating system. Yeah, so you generally don't use this directly. It's extremely inefficient and not performant, but you trust that allocators that people build will use this under the hood. So we've seen 4 allocators. There are actually a lot more. So there's a very performant allocator called memalloc, I believe. If my Wi-Fi works. Okay, it doesn't work, but this is also available in Zig. Yeah, you see? So, and the thing is, let's say you want to change the allocation strategy to your whole program. You don't need to do anything. You literally just replace the allocator, and because all the syntax is the same, everything, your entire program will still work. You just change the strategy of your allocation. Yeah, and so this is the whole point of allocating in Zig, is the fact that like everything goes through this allocator, and you can change your strategy as and when you want. You can even use the C allocator by doing, I forgot how exactly you use it. I think it's like .system allocator or .c allocator or something. But literally the same allocator as C, like malloc and free. Yeah. So let's explore a bit further on memory allocation. For the purpose of time, I won't run this, but you can literally copy and run this. But let's just see. So we have the same exact pattern here. We are creating our general purpose allocator. And now we're going to create an array list. So an array list is literally like a Java array list or a C, sorry, there's nothing in C, a C++ vector or a Rust vector. So it's a dynamic array that you can resize as and when you want. So again, you start by doing ArrayList.init, and notice that here we are passing in an allocator to the constructor of the ArrayList. This is saying that, hello ArrayList, please use this allocator to allocate your memory under the hood. And then, of course, whenever you init something, remember to de-init it. If you forget this, the compiler won't complain because Zig is a manually manage your memory in Zig. Yeah, so then you can append to the array list as per usual. But notice that every append has a try. And a try means that an error could happen. So what possible error could happen when you append to an array list? Any guesses? Exactly. So, and this is the same for alloc earlier. You see the alloc is actually a try. Yeah, so you can run out of memory. And this is why that every append in an array list, you need to try. You need to try it instead of just calling it. Yeah. So notice how when you remove something from an array list, and for those of us who use C++ vectors before, the reason this is called ordered remove is because there's also swap remove, which is, I believe, the thing that everyone wants to use to make their code faster. But anyway, so when you remove something from an array list, you're not actually allocating memory, so you don't need to try it. And this is like adding on to like the no magic idea behind Zig. Everything is explicit. You're very clear that this is going to allocate memory, and you're very clear that this is not going to do any allocations. It could still free memory though. Yeah, and to iterate through an array list, it's just dot items is the underlying slice. You just for dot items. Okay, so something interesting about this is that when you pass in an allocator to the array list, you need to store the allocator. And storing an allocator takes space. That means your array list from originally array list is just like, oh yeah, I'm storing an underlying slice and I'm storing like a capacity that's like 24 bytes. Right? But when you pass in an allocator, the allocator struct is literally another 16 bytes. So your array list grows and becomes like 40 bytes. Sometimes that's not what you want. And if you're copying this allocator everywhere, because remember everything in Zig is copied, if you're copying it everywhere, you literally have huge data structures everywhere. And sometimes you don't want that. So ArrayList actually gives ArrayList unmanaged. And what this means is that I don't pass in the allocator here. I'm going to pass it in every time I allocate memory. And this actually makes, so ArrayList unmanaged is 24 bytes. It doesn't store the allocator. But this means that very, very explicitly, every time I append, I need to pass in the allocator. But it literally does the same thing. In fact, ArrayList, the implementation of ArrayList is literally just ArrayList unmanaged, and then they store the allocator next to it. So literally the same thing. Okay, so that's memory management. Anyone has any questions? Okay, cool. So now we're going to working with C. So one of the big features of Zig is that it's super easy to work with C. And the whole point is that you are, with a gigantic C code base, you're supposed to be able to just introduce Zig right there and it will work. And to demonstrate this is a hello world using C printf. So, oh, how do you import C into Zig? Must be complicated. No, it's just C import and then C include and you're done. You can do c.printf and everything works literally as expected. I think. Let me check. 1, 2, 4. Okay, yeah. Yep, so it works. Mhm. Zig is the thing that's compiling the C code. No, Zig. I'm not too sure actually. I'm not sure whether it's using a pre-compiled like library or it's actually compiling the C code. Correct. Yeah, we'll talk about that soon. Oh, okay. Yes, and I'm not too sure, so I will just have to agree. Oh, so like they keep it like up to spec lah, versus like other like GCC or like CLang will be quite slow. Ah, okay, interesting. Okay. I didn't know that. Maybe I'll add it in later. I actually have a note. Hold on, where is it? Okay, yeah. So you would compile C programs using GCC, for example. GCC is literally Clang on Mac, which is quite funny. Wait. Yeah, it's alias, right? Oh, it's not. Okay, wait. Let's see. Yeah, it's literally. So GCC is literally Clang on Mac, which is quite funny. Yeah, it looks exactly the same lah. So, then if you want to compile the exact same code using the exact same flags, you literally just do zig cc, and then it literally does the same thing. What do you mean? I believe it's literally the same thing though. Yeah, it's literally the same thing. Like as in whatever works for Clang works for GCC works for Zig CC. Except that I guess what you mentioned like is probably more updated. Hmm. Yeah. Uh. Oh, yeah. Okay, interesting. I'll read more about that later. Um, okay, but going back to this, yeah. So it runs correctly, And if you want to try, so yeah, see for the rest of the page, we'll be working across multiple files. I'll give the file names here. So if we quickly create a C file, let me just demonstrate this. And you can follow along on your computers as well. So if you create a C file called greeter.h and greeter.c, doing all the standard C stuff. If you've never seen this before, like if you've never seen C before, this just defines a function that returns nothing and takes in a string, which is the name, and then it prints hello world if the name doesn't exist, or it prints hello like name if it exists. So to compile that, we would actually just do dash O is just the name of the compiled program, and then we just do this, and then we also have a main.c, which just greets three things: greets Alice, greets Bob, and greets now. So if we compile that, and if I cd into the correct directory, we can run, we get a greet program here, which is a binary file. And then we run that, we can see that it greets Alice, Bob, and Will. So as mentioned just now, the Zig CC literally does the same thing. Greet. And yeah, but this is still C. So there's nothing to do with Zig here. It's literally just a C compiler in Zig. So how do we integrate this with Zig? That is the question. So to integrate this with Zig, we need two things. So first, we need to build the Zig, build the executable by linking the Zig to the C code. And in order to do that, we need a build.zig file. So for those who are familiar with make files, this is kind of the same thing, except that you write it in Zig. So for example, this is literally saying to build my program, I'm building an executable, which is just a binary, and the name is greet, and then the path is just main.zig, which is the root source file. And this, you can just ignore this, these are just standard options. And we are adding the include path. This is for the .h file and its C source. So I deliberately kept my things separate. C source is my C files, and then source is my Zig files. And then the rest is kind of boilerplate, but basically it defines a command called run that will run this executable. I would recommend just copying this. There's not a lot of value in learning it now. So I'm going to delete what is going to be confusing. Actually, let me. Okay, let me have a clean instance. So you can see that now I have C source, source, and then the build.zig, which is literally just copy pasted from the example. Okay, and then I'm going to write the main file now. So the main file, very similar to just now, is going to import the C code directly. C import, C include, and then the C file. And the reason we don't need to specify where the C file is because we've already done it in the build file by saying C source, which is the include path. So for those of us who know C, this is like doing hash include on a C file, which is not a usual practice. But for this example, we're going to do that. And then we literally do the same thing. So if we look at our main.c and our main.zig, it's literally the same thing. And it even says null correctly. So if we check the type of the greet function, you see that it's actually a C pointer to a C string. And I believe what this means is that we allow nulls. And with some other like minor details that are related to C directly. And then we call literally the same thing and it works. To build and run this, you would do zig build, which triggers like, this is like saying make, right? So make is the same as zig build, and then we run. So it compiles the build script, and then it compiles the main file, and then it runs. And yay, we have our greet function working directly C code and Zig code. Quite interesting. I've never been able to show like working directly with another language in workshops because there's not enough time because it's always so complicated. Today is very interesting because I was like, wait, I can show this because like it's literally a few lines of code. So it's nice. And of course the boilerplate, but yeah, whatever. Okay. So now, any questions on working with C? Okay, so now to what I believe is the coolest feature in Zig, which is exploring comptime if my Wi-Fi works. I'm clicking on this. It's not going anywhere. Oh yeah, okay. Okay, so ignore the box. Let's create a sum. Okay, wait, hold on. I showed the answer already. Let's create a sum function that takes in a slice of numbers and returns the sum of all the numbers. Whoa, but it can be any type of number. It can be I32, I64, all that. So how can we do that? And oh, I forgot that I'm going to be presenting this. Okay, haha. I see you all reaching for your angle brackets. Woo. Yeah. So in Java, you would probably do something like I don't know, void. Wow, I forgot my Java already. Like that. Okay. Yeah. Okay. Yes, thanks. Okay. And probably you can't do it with integers also, right, in Java. Like you need like box the integer, this one, right? Okay. Okay, yeah, so something like this. But let me show you how to do it in Zig. So to do it in Zig, you define a completely normal function, except that you take in t that is a type. And then you take in a bunch of values, which is literally a slice of t. So this t could be literally anything. And then you just get a result of t equals to 0. And then for each value, you plus equals to the result. And then you return the result. Whoa, so cool. So now the thing is, when I call this function, I literally pass in what is the type of integers I want to sum, and it works. Or it should work if I didn't mess this up. Let me clean up, I say. Okay. So if I do this and I run, yeah. Okay, then I guess for F32s, there's a weird, this is E1, so it's basically times 10, so it's just 15. I don't know why it shows up like that. But yeah, so it's super cool, and there's this weird thing. This is probably the weirdest thing that is here. I guess like once you understand that t is like a type of integer, the rest of the code makes sense. So what exactly is comptime t colon type? Actually, slightly curious. Oh, okay. So we don't even need comptime. So what is t colon type here? So it turns out that in Zig, you can pass types around as values to a certain extent. So literally when I pass in I32 here, t is literally I32. If I, let's say, take in another type and I use it, I can literally do like assert t equals to u. And I pass in u32. Let's try this. So if I do that, it should crash because that t is not equals to u in this case. So it's literally like a value, right? And you can pass it around and you can do things to it. And why this is the case is because Zig defines this thing called comptime. So comptime is literally short for compile time. And to put it into context, it's very similar to macros in C, Rust, or Lisp. It is also very similar to generics in Java and Rust, or even like templates in C++. Yeah, for the C++ people, I'm not sure if I'm committing a sin to like lump them together, but there's templates. Or if you're using Go, you might have used Go generate before. probably one of the very like not less pleasant things I've done. Yeah. But the thing is, the comptime in Zig is a feature and a solution that literally encompasses everything above. You can generate code, you can do macros, and you can use it as generics in Zig. You've used it as generics earlier in the ArrayList example already. So a very simple, to start off with comptime, a very simple example is pre-computing values. So comptime is basically saying that it's basically allowing you to execute Zig code when you are compiling the code and not when you're running the code. So when you do Zig run, for example, which is probably a bad example, when you do Zig run, it's actually compiling it into an executable first and then running it. So Zig comptime is basically saying that I want to run some Zig code during that compilation process. And going back to our original example, literally exactly the same thing. However, I just do comptime sum instead. I literally change sum, here, sum, and I add a comptime in front. And this works like with or without like this weird t thing, right? And what this does is it executes sum at compile time, which means that at runtime within the binary itself, this will literally be already 1 plus 2 plus 3 plus 4 plus 5. And this will already be 15, and this will already be 15. So this sum code, this for loop will never run, at runtime. It will already be compiled as 15 into the binary. Yeah.
So what if let's say your sum I32 wasn't statically defined like over here, let's say you read a series of numbers from on this network. Then what would be the result of
Mm.
time?
So you can't. So the answer is that you can. Comp time is limited, obviously. So you can't do two complex things. For example, accessing external resources. There are some ways you can. You can access a file, I believe, in comp time by using some add something like some compiler directive add something. But I don't believe you can like directly read a file and do all that. Yeah. So it's limited, and the reason we can do it here is because sum is a pure function. It kind of doesn't access any like state or any global variables or anything. It just calculates output from its input. Yeah. So in the case of the example he gave, which is like reading from a file usually allocates memory. And allocating memory is something you can't do at compile time. So it already like the compiler will detect like this calls this, calls this, calls this, calls memory allocate. You can't do it at comp time. Yeah. Yeah, it's sort of like to generate code, sort of the thing. So for example, how it works here how comptime works here is that when a compiler detects this, it says, okay, you've passed in 3 functions. It will actually create 3 sum functions. So it will literally sum underscore underscore I32, sum underscore underscore F32, sum underscore. It copies the function 3 times. So yeah, so one of the things I guess is that like your binary size will increase because it's copying the function multiple times. So this is pre-computing values. Very, very simple use case. Could be useful if you are doing things like you just want the the logarithm of a number like as a constant, or you want to generate constants. Like your constants are all like related. Like your global variables are all related. You can pre-compute them all at compile time. Various other things. But probably a more useful thing is generics. So here I'm creating a vector 2D, but of any type. Right. So just to copy this over, generics. So here vector 2D is basically a vector of 2 numbers, x and y. And I'm saying that vector 2D is actually not a struct. It's a function that takes in a type and returns a struct. So now suddenly the const sum struct equals to struct makes sense now. Because actually structs are literally, because types are values, or types act like values, this is actually a value, an expression. and you can return it and do anything to it. I can also do like const u equals to this and then return u, and it works. This can be a union, works as well. This can be enum, changing whatever's inside lah. It works as well. So that's why the syntax was why it was earlier, going back to what I said at the start. And this vector2d is a function. So you call it like a function. So I can do const vector2d of i32s equals to, and I literally call the function because it's just a function. And I can do that. I32. And it works if I spell correctly. Wow, okay. So suddenly you unlock a whole lot of things you can do with this. For example, you can, so the thing is like, okay, sure, like you might be like, oh yeah, this is basically your angle brackets, right? But I can take in anything. I don't have to take in a type. I can take in a length as a u size, for example. And I can literally plug it in as the type of the array. And it works. So now suddenly we have length generic vectors as well. Oops. It's right here. Okay. Wow, and I can do vector i32 2d, which is 2, and then vector f32 4d, which is 4. And these will all construct correctly and compile correctly. For example, if I exclude one of them, it fails because destination is length 4, source is length 3. Right? Because that it's literally a 4f32. Yeah, so this is one such example. Another such example, if we look at what was the one? If you look at the general purpose allocator, let's go back to this example. Notice how this is actually the general purpose allocator, and this just constructs it, right? So if we go inside the source code, we can see that general purpose allocator is a function very similar to what we just did that takes in a config. And this config is not a u size, it's not a type, it's literally a struct of like settings that we can change. Config. But the thing is, this is all done at compile time. So this config, should I have stack trace, the number of stack trace frames, should I enable memory limit? This isn't configured at runtime when your program runs. This is all done by the compiler before it even runs. So that's something that's super powerful, and you can abuse it as well, but it's super powerful. So that's generics. And that's all the content I prepared, but I can have another example. Okay, we can explore array list as well, one of my intentions. So we're going back to all the stuff that we did earlier. And array list is a function that takes in a type and then returns a type. Okay, so we are about time right now, but I will do one more example, which is to let's try to write a function that let's try to write an array list that only takes in values that have a field called x. So that means if I do, okay, wait, let me do a new file. So we have our type array list, right? And okay, sure, like, okay, maybe we just do a vector to be simple. So struct values, maybe we'll fix this. Okay, just now the vector that we had, right? Okay, so now let's say I want this to work, so vector 2d. Let's define a new struct. Foo equals to struct x. Okay, and then struct y. Okay, so we have two structs, and then one has x, one has y, right? I want vector to be able to take in. Okay, let's just fix this at 2 to be simple, and then this returns a type. I want this to be possible, so vector of i32s vector of foo. But I want this to be a compile error. So this should fail. So maybe as a final exercise to everyone, can anyone think of where I should write code to sort of make this fail? Because right now it passes, right? Because this and this are literally the same. So where, like, which line should I start writing code in to sort of constrain this and make this fail? Think about it as like you're writing a Zig program. You're not doing any comptime or weird stuff. Anyone guess?
So you want a vector of bars to fail.
Correct. Like I want this to be a compile error.
You assert that in the vector function
Mhm.
that that your key is not
Ah, okay. Yeah, that's perfect. So if t equals to bar, I want a compile error. No way. Okay, and so one of the quirks about Zig is that code will not actually like the compiler will not actually touch code unless you use it. So you kind of need to use it. So I'm just gonna use it. Vector of fools. Vector of bars. Okay, now let's try this. Oops. This is just a demo anyway. Whoa, correct, right? Because we don't want because t equals to bar, but if I comment this out, works. Nice. Okay. So this was oh yeah, sorry. Okay, so this was low-key hacky because that means vector needs to know that bar exists. So I want accept any type, only types that have an x field.
like your if statement just now. Like won't it also be run in runtime? It's just an empty if statement.
No, it runs at compile time. And the reason it runs at compile time is because it uses types in its expression. And the compiler can detect that. So your types do like this cannot exist at runtime.
So what if you in the if statement if you combine types and let's say you check for another let's say another parameter which is let's say integer. So how would it work at runtime?
Like x u size is it? So if t is it just won't allow, it'll fail. Yeah. Okay, so I haven't taught this during the workshop, so maybe only if you Google you'll probably find it. But you can literally like it has few x. If not has field x bye. And then this should work. Yep, perfect. And it tells you this as well. Okay, so this seems very contrived and kind of because I came up with it on the spot as well. But if you look at the Zig hash map, maybe if I go to what's a good way to do this? Okay, so if you go to the hash map implementation in Zig, and then you go into so it's a generic function as well, and then you see that, oh, there's this comptime context type, right? So it's a namespace that provides two functions, hash and equal. But you think that, okay, yeah, sure, this is like a comment that you just have to make sure that yourself. But no, there's a verify context. I've been lied to. Hash map, sorry, yes, this one. See, so there's a verify context type function that literally checks, make sure that you have a hash context must contain hash and equal member functions, or like this one is one. And if the verify function fails, it will give a compile error. So this is just some of the, and then another example of comptime. Correct, yeah. So you can make sure stuff only runs at comptime as well. Okay, so that's the last thing I have for you guys today. So hopefully that through this you have learned something, and feel free to approach me after this to like ask random questions as well. Thank you for all the questions that I've gotten today, by the way. They're all really, really good. And yeah, hopefully this inspires you to learn more stuff and learn Zig and use Zig in your programs. Yeah. And publish whatever you do, because you never know when some random recruiter might find you or something. I don't know. Yeah. That's all. Thank you so much.